There's a strong intuition that greater ignorance justifies delaying a decision or opting for a default, whereas greater knowledge justifies greater decisiveness. This intuition has two common manifestations. First, a tendency to want to keep on doing what we're doing unless there's compelling certainty about the need to change. Back in the 1970s, when it still was not clear whether chlorofluorocarbons, known as CFCs, were damaging the ozone layer, industry leaders and their lobbyists argued that a ban on CFCs would be prohibitively damaging to the economy, so therefore their manufacture and sales should continue until greater evidence was obtained of their effects. When this tendency is strong enough that people refuse to change even when change is desirable, it's known as status quo bias. A second manifestation is to do nothing until more knowledge comes to hand. The key idea here is using unknowns to justify delaying a decision. Of course, doing nothing can be a default choice on its own, and sometimes is equivalent to sticking with the status quo. In the case of climate change, inaction is tantamount to maintaining the status quo, that is, continuing to add CO2 to the atmosphere. We've seen appeals to uncertainty in climate science as arguments against taking costly actions to reduce emissions or otherwise militate against global warming. And we've already seen from the interview with Michael Moore that delay is a favored strategy for politicians in the face of uncertainty. Moreover, we're more likely to delay a decision when it is really important. Our intuition tells us the more important decisions should take more time and effort than unimportant ones. A series of experiments have demonstrated that this intuition persists even when deferral does not provide more flexibility, when it presents potential disadvantages, and even when it is financially costly but has no financial benefits. When might it be a bad idea to delay decisions or actions because of ignorance? A compelling example was provided by a student when we ran this course for the first time. A mountaineer, scaling a sheer rock face, finds himself at an impasse. Moving upward bears a great risk of falling, but so does moving downward. It isn't clear which move is the riskier. As he clings to the cliff face, his reserves and strength are fading. The one thing he should not do is delay making one move or the other, because the longer he waits, the weaker he will be, and the less likely to make his move without falling. Let's examine an example where we can quantify the consequences of delay. You have a debt of $10,000, and your current interest rate for repaying this loan is 5% of whatever remains to be paid. You can afford to make a repayment of $700 in each payment period, and that's tolerable because, as you can see in this graph, you'll eventually pay off the loan in 28 payments. Interest rates are not fixed, and you know that the bank is going to increase the rate in the next pay period. However, you have some uncertainty about how large the increase will be. Suppose you have good evidence that it won't be more than a 2% increase. Then you'll end up in the borderline situation in the graph. Your debt won't be repaid, but it won't increase either. Suppose you have a nest egg of $3,500 that you'd be willing to sacrifice to speed paying off the debt. You could contribute that $3,500 at any time, reducing the debt to $6,500, and then your $700 repayments will repay the entire debt within 16 pay periods. Delay does matter here. You'll pay more if you delay the $3,500 contribution, but it isn't fatal. But now imagine that your uncertainty about the interest rate increase is greater than a 2% interval. If it could be as large as 3 or 4%, then you're in trouble, as the bad and worse curves demonstrate. With your current repayments of $700, your debt is going to grow, and it will compound. Now it really matters when you contribute your nest egg. If you wait longer than the 6th pay period, then you won't be able to repay the debt at 8 or 9% interest. If you wait until the 6th payment period, $3,500 is sufficient to reduce your debt to the point where $700 every pay period will pay it off if the new interest rate is 8%, but not if it's 9%. It is only if you commit by the 2nd period that $3,500 will suffice to render your debt payable if the interest rate is as high as 9%. The critical point here is that some kinds of situations with greater uncertainty require greater action. Delay makes the situation worse. The considerations illustrated by the debt example are important in many kinds of situations. I'll start by looking at the banking industry and then turn to climate change. I've been a statistical consultant to the banking industry and involved in building models to predict annual bank losses. The bank uses these models to decide how much capital they should retain to self-insure against these losses. Suppose that for a particular business line, a bank decides they wish to retain enough capital to insure against a loss that the model says is less than 5% likely to be exceeded. Actually, most banks would find 5% far too great a risk, but I'll use it for illustration here. In this graph, we have models from two hypothetical scenarios. It may not look like it, but both models predict the same average loss, $268,337. However, they differ in their estimates of the variability of the losses. One predicts a standard deviation, a statistical measure of variability and therefore of uncertainty, of about 352,000, and the other predicts about 782,000. So the second model has greater uncertainty. How does this greater uncertainty influence the estimated capital that the bank should retain? If we look at another graph, this one showing how likely losses will exceed the values on the horizontal axis, we can see that for the lower loss values, the model with less uncertainty is more likely to exceed them than the model with greater uncertainty. But for large losses, the two models reverse. Taking a close-up view of the upper part of the graph, we can see that the 5% cutoff for the less uncertain model is about $840,000, whereas for a more uncertain model, it's around $1,020,000, a substantially larger amount of capital for the bank to retain. The cause of this counterintuitive result is the fact that the bank losses are skewed, with a long tail in their distribution. As the variance increases, this tail stretches farther into the extreme loss values, even if the mean stays the same. We've just seen an example of this because you'll recall that the means of both models were identical at $268,337. In 2014, Stefan Lewandowski, James Risby, Ben Newell, and I applied the logic I've just explained in the banking scenario to taking action against global warming. We put the case that more uncertainty about the severity of global warming does not justify continuing the status quo, but the opposite. It implies greater urgency for action. The next graph shows 4 illustrative models of global warming estimates, each of them predicting the likelihood that warming will exceed 5 degrees within a certain time period. This is a threshold that, if exceeded, results in very severe consequences for humanity and other species. Like my bank loss models, these models all have the same mean, approximately 3 degrees, but they differ in the standard deviations. The larger the standard deviation, the more likely it is that the 5-degree threshold will be exceeded unless we start taking measures to reduce emissions now. To give an idea of how unbelievable this logic is to many people, consider the following blog post in response to Professor Ian Enting's commentary on our papers, where he says, "What the two papers do is add an extra layer by pointing out that the greater the uncertainty, the worse on average will be the consequences. Thus, by implication, the greater the uncertainty, the greater the need for action. Part of this comes from the form of the uncertainty with greater uncertainty at the high end. What is an important part of the paper in climatic change is the nature of damage from climate change. This gets progressively worse, more rapidly than the temperature increase. The consequence is that with greater uncertainty, the average projected damage will increase." Ian Enting, Honorary Senior Associate, Faculty of Science at the University of Melbourne. Professor Enting's summary garnered this one-liner. "Say what? The consequence is the greater uncertainty, the average projected damage will increase? Where's the logic in that statement?" There's also another problem. Around the same time as the work described above was published, David Budescu, Han-Hui Por, Stephen Brumell, and I reported the results of a 24-nation, 17-language study spearheaded by Professor Budescu of laypeople's interpretations of probability phrases used in the Intergovernmental Panel on Climate Change reports to describe uncertainties in climate change science. Here are 2 examples of the sentences from the IPCC fourth report that were used in this study. The probability phrase is very likely, and the IPCC authors specified that very likely means a probability of 90% or greater. However, when people were asked to nominate their best estimate of what probability they thought very likely referred to, the typical estimate was around 71 to 72%, well below the IPCC 90% minimum. When asked for the lowest probability they thought this phrase could mean, the average was 56 to 57%. This was the case for the 4 IPCC expressions investigated: very likely, likely, unlikely, and very unlikely. In this graph, the boxes show the middle 50% of people's best estimates, and we're talking about a total sample size of over 10,000. The IPCC threshold guidelines are the blue horizontal lines. You can see that for all four expressions, most people's estimates are much closer toward the middle of the scale than the IPCC guidelines. These findings held up regardless of language or culture. These two sets of findings interconnect in the following way. If people believe that greater uncertainty justifies less inclination to act, and if they attribute more uncertainty to climate science than is the case, then we're in double trouble when it comes to persuading the public that mitigation of global warming is an urgent issue. In this lecture, we've examined cases where greater uncertainty requires earlier, stronger intervention rather than the most common responses of delay or inaction. We've seen that such cases can arise in personal matters such as debt repayments, business concerns such as bank losses, and even environmental issues such as climate change. What do these cases share that distinguishes them from those in which inaction or delay is advisable? They are all situations in which the expected negative consequences increase non-linearly as uncertainty increases. In the debt scenario, this is due to how interest compounds over time. In the banking and climate change scenarios, it's due to how losses or damage scale up relative to variability. Here, uncertainty most certainly is not our friend.